It is amazing to think that as recently as the beginning of the 20th century, there was still a great deal of debate surrounding the existence of atoms. Those who doubted their existence cited the simple fact that they could not be directly observed, and therefore how could we possibly conclude that they exist? Whereas those who supported the atomic hypothesis referred to the remarkable success of the kinetic theory of gases, which was able to account for the macroscopic properties of gases by assuming that they were comprised of trillions upon trillions of tiny atoms in random motion. The reason we couldn't see the atoms was simply because they were too small. However, the debate was short-lived. A series of remarkable experimental observations at the beginning of the 20th century could only be explained using the atomic theory, and furthermore, it was realised that the structure of the hypothesized atoms could be used to explain the incredible diversity of the properties of material objects in the natural world. When, in 1897, J.J. Thomson proved by experiment that tiny negatively charged particles called electrons can be extracted from atoms, leaving behind positively charged ions, it became clear that atoms are not, as the Greek meaning of their name implies, indivisible constituents of matter, but rather complex systems formed by positively and negatively charged parts. In 1904, Thomson proposed a model of the atom in which he visualized the atom as being formed by some positively charged substance uniformly distributed throughout the atom, with negatively charged electrons embedded like plums inside a pudding. However, the model was not without its problems. Whilst it was possible to derive some stable configurations of motionless electrons embedded in the positively charged medium, he suspected that it was the motion of electrons inside atoms that was responsible for the properties of magnetic materials. However, his model was incapable of accounting for the motion of electrons within the atom. The experiment that ultimately caused the death blow to the Plum pudding model was the famous alpha scattering experiment of Geiger and Marsden in 1909, which involved firing a stream of positively charged alpha particles at a thin piece of gold and measuring the angles of deflection. According to Thomson's model, if you fire high-energy alpha particles at a thin gold leaf, then you should find that practically no alpha particles are reflected by the gold. This is because the diffuse positive charge filling Thomson's atom would provide minimal repulsive force, and therefore be unable to deflect alpha particles back towards the source. However, when Geiger and Marsden performed the alpha scattering experiment, they found that roughly 1 in every 8,000 alpha particles were deflected back towards the source, in direct conflict with Thomson's prediction. In March 1911, Ernest Rutherford proposed a radical new model of the atom in order to account for the experimental results of Geiger and Marsden. According to Rutherford's model, the atom consists of a tiny positively charged nucleus, surrounded by even tinier negatively charged electrons, which occupy the vast regions of space around the nucleus. This explained why most alpha particles pass through the gold leaf, since they are simply passing through the vast regions of empty space within the atoms of gold. However, in those rare cases where an alpha particle collides head-on with the gold nucleus, the concentration of positive charge within the nucleus is sufficient to push the alpha particle backwards, and this accounts for the 1 in 8,000 alpha particles that were scattered back towards the source. Although Rutherford's model was a significant improvement over Thomson's, it was plagued with problems of its own. If the electrons are believed to exist in the space surrounding the nucleus, then what exactly are they doing? They can't just be standing still, because the electrostatic force of attraction between the positively charged nucleus and the negatively charged electrons would surely cause the electrons to be pulled into the nucleus, and this would imply that all atoms are inherently unstable and therefore should collapse. The obvious solution to this problem is to propose that the electrons are in fact orbiting the positively charged nucleus, much like the Earth orbits the Sun, and that it's the orbital motion that prevents the electrons from falling into the nucleus, just as the motion of the Earth stops our planet from falling into the Sun. However, the orbiting electron model doesn't work either. To see why, we need to refer to Maxwell's theory of electromagnetism, which had been developed in the second half of the 19th century. According to electromagnetism, surrounding every charged particle there exists an electric field, and if you change the position of a charged particle, then the field will also change. Now, according to electromagnetic theory, if a charged particle moves in a circular orbit, then the acceleration of the particle will cause a ripple in the surrounding electromagnetic field, corresponding to the emission of electromagnetic radiation. If we apply this to an electron orbiting the nucleus, then we see that as the electron orbits the nucleus, it will radiate energy, and therefore as it loses energy, it will slow down and spiral into the nucleus. And electromagnetic theory predicts that this would occur in less than a trillionth of a second. So it appears that the electron cannot be standing still, and it cannot be orbiting the nucleus like a planet orbits the Sun. So what exactly is it doing? The answer to this question would require a union of the old classical ideas of electromagnetism with the newly developed ideas of energy quantization, as put forward by Max Planck and Albert Einstein. And it would require the remarkable vision of one man, Niels Bohr, who would become one of the founding fathers of quantum mechanics. In 1911, after completing his PhD at the University of Copenhagen, a 25-year-old Niels Bohr joined J.J. Thomson at the Cavendish Laboratory in Cambridge with the hope of working with Thomson on the structure of the atom. However, folklore suggests that J.J. Thomson and Bohr's relationship did not get off to the best of starts when, during their first meeting, Bohr apparently entered Thomson's office with a copy of one of Thomson's books on atomic structure, pointed to a particular section and declared, "This is wrong." It is hardly surprising, therefore, that Thomson did not immediately warm to him. A number of disagreements between the two men forced Bohr to abandon Cambridge and head for Manchester, where he had been invited by Rutherford himself. Like Einstein and Planck before him, Bohr realised that attempting to resolve the problems of the atom using purely classical physics was probably doomed to failure. Instead, he should take seriously the idea that energy is only ever transferred discretely in chunks, or quanta, rather than in the continuous fashion predicted by classical physics. Furthermore, Einstein's explanation of the photoelectric effect in 1905 had demonstrated that light should be considered a stream of particles, called photons, each consisting of a discrete amount of energy. Faced with the challenge of the stability of the atom, Bohr took a leap of faith and simply hypothesized that in order for atoms to be stable, there must exist stable configurations of the electrons orbiting the central nucleus, and that these stable orbits should depend, in some as yet unspecified way, on Planck's constant. Furthermore, he suggested that the transitions between these stable states would cause the emission of photons of discrete energy. Young, enthusiastic, and unhampered by the limitations of classical physics, Bohr launched into a period of intense productivity, resulting in the publication of 3 papers in 1913 that would change the landscape of atomic physics forever. Bohr's groundbreaking work focused on the simplest atom, hydrogen, and was based on 4 postulates that combined elements of classical and quantum physics. The first was based on Coulomb's law from classical electrodynamics. According to this postulate, the electron is held in orbit around the nucleus by the Coulomb force of attraction between the positively charged nucleus and the negatively charged electrons. The second postulate is the assertion that, contrary to predictions of electromagnetic theory, the electron does not radiate energy despite the electron's acceleration. The second postulate removes the problem of the stability of an electron by simply postulating that this particular feature of the classical theory is not valid for the case of an atomic electron. This postulate was based on the fact that atoms are observed by experiment to be stable, even though this is not predicted by the classical theory. This may seem like a rather bold assertion, but Bohr was hopeful that the exact mechanism explaining how this is possible would emerge later. The third postulate introduced the idea that the angular momentum of the electron is quantized in units of Planck's constant divided by 2 pi, and the final postulate suggested that photons of light are emitted by atoms whenever an electron moves from a higher energy orbit to a lower energy orbit. The justification of Bohr's postulates, or of any set of postulates, can only be found by comparing the predictions that can be derived from the postulates with the results of experiment. So we will now consider these ideas in a bit more detail. We will begin by looking at the quantization of angular momentum. According to classical physics, the angular momentum of an orbiting electron is found by multiplying the mass of the electron by the vector cross product of the radius and velocity vectors. Furthermore, the magnitude of the vector cross product of any 2 vectors is given by multiplying together the magnitudes of the individual vectors and the sine of the angle between them. In the case of an electron in a circular orbit, this angle is always 90 degrees, and therefore sine of 90 equals 1, and we see that the angular momentum is equal to the mass of the electron times the velocity times the radius. Now, we see from this expression that according to classical physics, because the radius and velocity can vary continuously and take any value, so too can the angular momentum. However, Bohr proposed that the angular momentum of the orbiting electron is quantized in integer multiples of Planck's constant divided by 2 pi. If we combine the classical and quantum expressions for the angular momentum and rearrange for the radius of the electron orbit, we find the following expression. Before we can fully appreciate what this equation is saying, we need to find a way of describing the motion of the electron in its orbit around the nucleus. Bohr assumed that the electron was held in its orbit around the nucleus by the Coulomb force of attraction between the electron and the proton. Coulomb's law states that the magnitude of the force acting between two charges Q1 and Q2 is proportional to the product of the charges and inversely proportional to the square of the distance between them. Applying this to the example of a single electron of charge E orbiting a single proton of charge E, the electrostatic force is given by the following expression. Next, we assume that the electron is orbiting in a circular path of radius r with speed v. Because the direction of the electron is constantly changing, the electron must be accelerating, and therefore, according to Newton's second law, there must be a resultant force directed towards the centre of the circle that is causing this acceleration. In the case of circular motion, the centripetal acceleration is given by the expression a equals v squared over r, and if we combine this with Newton's second law, we find the following expression for the centripetal force acting on the electron. Bohr assumed that the centripetal force was provided by the Coulomb force of attraction, and therefore he equated these two mathematical expressions to arrive at an equation for v squared. Next, he used the expression derived for the radius using the angular momentum quantization condition. If we square this expression and substitute the blue equation for v squared, we arrive at the following equation, which tells us the radius of the allowed electron orbits. Let's take a closer look at this equation. We see that the electron is only allowed to orbit the nucleus at certain distances, depending on the value of n. If we substitute the appropriate values for Planck's constant, the permittivity of free space, epsilon naught, the mass of the electron, and the charge of the electron into this equation, we find that for n equals 1, the so-called Bohr radius is calculated to be 0.53 times 10 to the minus 10 meters, and this provides a rough estimate for the atomic dimension of the hydrogen atom. When Bohr calculated this value, he was reassured that the value he found on the basis of angular momentum quantization was in line with other known estimates for the size of the atom. If we next calculate the radius of the n equals 2 and n equals 3 orbits, then we see that the distance between adjacent orbits grows as n increases. Another thing that Bohr was able to calculate was the orbital speed of the electrons. Recall that we were able to derive an expression for the speed of the electrons using Coulomb's law. If we then substitute r into this equation, we find the following expression, which can be used to calculate the speed of the electron in different orbits corresponding to n equals 1, n equals 2, and so forth. Clearly, the fastest possible speed will correspond to the innermost orbit when n equals 1. In that case, we find a speed of 2.18 times 10 to the 6 meters per second, which is reassuringly less than the speed of light. And so Bohr was pleased to see that his model of the atom did not appear to violate Einstein's theory of special relativity. Once Bohr had determined the radii of the allowed electron orbits, his next task was to determine the energy of each of these orbits. In order to do this, he realized that the total energy of the electron will simply be the sum of its kinetic energy and potential energy. The kinetic energy is due to the motion of the electron, whereas the potential energy is due to the electrostatic force of attraction between the electron and the positively charged nucleus. Now, the kinetic energy is easy to calculate, as I'm sure you remember from school. It's simply given by half times the mass times the velocity squared. The electric potential energy is derived from Coulomb's law, and for the hydrogen atom is equal to minus E squared over 4 pi epsilon naught r. Why the minus sign? Well, the minus sign is there because the convention in physics is to define the potential energy at infinity to be 0, and since the potential energy of the electron increases as it moves further away from the nucleus, it must be negative for finite separations. So if we add these two equations together and substitute the following expressions for v squared and r, which we derived earlier, then we find the following yellow expression, which simplifies in the following way. Note that all of the terms inside the bracket are constants. If we substitute the experimentally determined values for each of these constants, we find that the combination of terms inside the bracket corresponds to a numerical value of 2.18 times 10 to the minus 18 joules. And so we can write the total energy of the electron as minus 2.18 times 10 to the minus 18 joules divided by n squared. This equation tells us the energy of the electron in each of the allowed orbits corresponding to n equals 1, n equals 2, n equals 3, etc. As you can see from this equation, the orbital energies are very small, and therefore physicists often write the energy using a different system of units called electron volts rather than joules. An electron volt is defined as the energy transferred to an electron when it is accelerated through a potential difference of 1 volt. So for example, imagine you had two parallel conducting plates connected to a 1 volt battery. If you placed a single electron at the negative plate, it would clearly experience a force and accelerate towards the positive plate. And the amount of kinetic energy it gained moving between the plates is what we define as an electron volt's worth of energy. In order to calculate how much energy in joules an electron volt corresponds to, we can make use of the definition of potential difference, which is defined as the energy transferred per unit charge. If we rearrange this equation, we find the energy transferred is equal to VQ. So in the case of an electron, with charge E moving through a potential difference of 1 volt, we see that the energy transferred equals 1.6 times 10 to the minus 19 joules, and this is what we call 1 electron volt. So 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. If we now rewrite the total electron energy in electron volts, we find the following famous equation, E equals minus 13.6 over n squared electron volts. And this equation tells us the energy of the nth electron orbit. Now if we calculate the energies of the first 6 orbits, then we find the following values. We see that the energy difference between adjacent orbits decreases as n increases. We can picture these orbits in a number of ways, but it is often convenient and conventional to represent the energy levels as a series of parallel lines with the lowest energy, also known as the ground state energy, at the bottom. As the electron moves away from the ground state, its energy increases, and an infinite distance from the nucleus, the energy is defined as 0. Bohr realised that in order for an electron in the ground state to move to a higher energy state, it would need to absorb just the right amount of energy, corresponding to the exact difference between two energy levels. When an electron moves from a lower to a higher energy level, it is said to be excited. So for example, imagine that an electron is excited from the ground state to the n equals 4 energy level. The question Bohr then asked was, how does the electron lose energy such that it can return to the ground state? It was at this stage that Bohr delivered his master stroke. He realised that the electron loses energy by emitting a photon, and that the energy of the emitted photon is equal to the difference in energy between the higher and lower energy level. The greater the energy difference, the greater the energy of the photon. Bohr also realised that there were often more than one route that an excited electron could take in order to return to the ground state. In our example, we see that the electron could hop between every level on its route to the ground state, or it could move from the n equals 4 to the n equals 3, then the n equals 1 level, or it could move from the n equals 4 to the n equals 2, and then from the n equals 2 to the n equals 1, or it could go straight from the n equals 4 to the n equals 1, and each of these different transitions would correspond to the emission of a photon with a particular amount of energy. Let's now look at this in a bit more detail. Imagine that an electron in the ground state is excited to the n equals 2 energy level. When it de-excites and drops back down to the ground state, it will emit a photon, And as we know, the energy of a photon is given by the equation E equals hf, or E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. We can work out the energy of the emitted photon by calculating the difference in energy between the n equals 2 and n equals 1 level. If we put in the numbers, we see that the energy difference is equal to 13.6 minus 3.4, which is 10.2 electron volts. And if we convert this into joules, we find that the energy difference is 1.63 times 10 to the minus 18 joules. So this is going to be the energy of the emitted photon. We can work out the wavelength of the emitted photon by using the equation lambda equals hc over delta E, and we find that the wavelength turns out to be 122 nanometers. So what kind of photon is this? Well, the wavelength of the photon tells us about the type of radiation emitted. Visible light has a wavelength of between roughly 350 and 750 nanometers, with violet light being at the short wavelength end and red light being at the long wavelength end. Wavelengths slightly longer than 750 nanometers take us into the infrared region, and wavelengths slightly shorter than 350 nanometers take us into the ultraviolet region. And therefore we see that the 122 nanometer photon is an ultraviolet photon. In other words, photons emitted as a result of this particular transition are not directly visible. Likewise, electron transitions from the n equals 3, 4, 5 and 6 energy levels down to the ground state will all cause the emission of ultraviolet photons. This series of wavelengths is referred to as the Lyman series, named after Theodore Lyman, who first discovered them. The natural question to ask at this stage is whether any electron transitions correspond to the emission of visible photons, and the answer is yes. We are going to consider electron transitions from the n equals 3, 4, 5 and 6 energy levels down to the n equals 2 energy level. Let's see what we get. Firstly, if we calculate the wavelength of the photon emitted when an electron moves from the n equals 3 to n equals 2 level, we find a value of 654 nanometers, and we see that this corresponds to a reddish colour in the visible spectrum. Next, if we consider a transition from the n equals 4 to n equals 2 levels, we find a photon of wavelength 488 nanometers, and this corresponds to a light blue-green colour. The n equals 5 to n equals 2 transition corresponds to a wavelength of 435 nanometers, which is a deep blue colour, and finally the n equals 6 to n equals 2 transition corresponds to a wavelength of 412 nanometers, which is a purple-violet colour. And in terms of visible photons, this is it. You can try calculating the photon wavelengths for all other possible transitions within the hydrogen atom, and you will see that these are the only 4 transitions that cause the emission of visible photons. And so rather than having a continuous spectrum of colours, we actually have what is known as a line spectrum, consisting of 4 lines of colour. And the wavelengths corresponding to these 4 lines are unique to hydrogen, a bit like an atomic barcode. These 4 visible lines are named the Balmer lines, after Johann Balmer, who discovered an empirical equation to predict the Balmer series in 1885. It had long been known that if you pass the white light emitted from a hot object, such as the sun or a filament lamp, through a triangular prism, then the light will disperse and a continuous spectrum of colours will be observed. However, detailed experimental investigations in the 19th century revealed that the light emitted from a glowing gas of a particular element does not form a continuous spectrum. So how do you make a gas glow? Well, that simply involves taking a rarefied gas and passing an electric current through it. Collisions between the electrons flowing through the gas and the atoms of the gas cause the gas to emit light. If you then pass that light through a triangular prism, what do you get? Well, in the case of hydrogen gas, you observe the following pattern, and if we overlay the colours predicted by Bohr's model of the atom, we find remarkable agreement between the colours and wavelengths of light. Note that the purple-violet line cannot be seen in this picture, and this is simply because this particular emission line has a very low intensity, which was not picked up in this particular photograph. One of the remarkable successes of Bohr's model of the atom was its ability to explain the hydrogen emission spectrum. We see that these unique lines are simply a result of electron transitions between discrete energy levels inside the hydrogen atom. and that the discrete energy levels are a consequence of the angular momentum quantization condition. So we see that introducing the quantum into the atom not only helped to stabilise the atom, but also helped to explain the emission spectrum of the hydrogen atom. But it wasn't only the hydrogen atom that could be explained using the Bohr model. The basic idea of energy levels and electron transitions would ultimately account for the emission spectra of all the known elements in the periodic table, and Bohr's model would be hailed as a triumph, for which he would be awarded the Nobel Prize in 1922. As is often the case in physics, the solution to one set of questions naturally gives rise to a new set of questions. Bohr wrote to Rutherford on the 6th of March 1913, enclosing with his letter a manuscript with the title On the Constitution of Atoms and Molecules. In his reply, Rutherford reacted favourably but raised some difficult questions. He was particularly puzzled by the fact that, in Bohr's model, an electron in a high-energy orbit would somehow need to know beforehand the energy of the final destination in order to emit radiation of just the right wavelength. In this simple statement, Rutherford was raising the alarm about the implications of the new quantum theory for our understanding of cause and effect, and this alarm would continue to sound for the remainder of the century and well into the next. The success of the Bohr model, as measured by its agreement with the experiment, was certainly very striking, but it only accentuated the mysterious nature of the postulates on which the model was based. Where did the angular momentum quantization condition come from? And what was the mechanism behind electron transitions between energy levels? The answers to these questions would have to wait nearly a decade, until the beginning of the 1920s, when the pioneering work of de Broglie, Schroeter, Heisenberg and Dirac would lay the foundations for the most successful theory ever created on Earth, quantum mechanics. Our vision of reality would never be the same again. Reflecting on this fact, Bohr said, "We must be clear that when it comes to atoms, language can be used only as in poetry. The poet too is not nearly so concerned with describing facts as with creating images and establishing mental connections. Physics is not about what the world is, it is about what we can say about the world."